Hello, my name is Bhavin Shah, and in this demo, we'll talk about how Portworx Kubernetes storage can provide features like high availability, encryption, IO profiles, etc. to Tanzu Data Services that are running on your VMware Tanzu Kubernetes cluster. So for this demo, we have deployed a single TKGS cluster with 5 worker nodes, and we have already deployed Portworx version 2.8 on the TKG cluster. This means that Portworx has automatically provisioned VMDK files with the size that we specified and aggregated those individual VMDK files across nodes into a single storage pool that can be leveraged by stateful applications that are deployed on the Tanzu Kubernetes cluster, which in this case are Tanzu Data Services. For deploying these data services, we have deployed individual namespaces. So there is a namespace for MySQL, for PostgreSQL, for VMware Tanzu RabbitMQ, and then VMware Tanzu Greenplum. And then we have used their operators and then deployed individual instances for each of these applications. At Portworx, we understand that each application has different requirements when it comes to the storage layer or the persistent layer. So by configuring different storage classes for each of these individual applications, operators can control settings like the replication factor, the high availability factor, whether you want your data encrypted or not, what kind of IO profile to associate for that specific application. All of those features are things that we look at in this demo. Now let's switch to Octant and look at our cluster details or look at our cluster overview. As we already discussed, we have created individual namespaces for each of our VMware Tanzu data service. So navigating to the namespaces tab, we'll get a list of all the different namespaces that exist in our cluster. So we have created different namespaces for the data services operators, and we have created namespaces for those data service instances. So RabbitMQ system hosts the operator, and then RabbitMQ is where our RabbitMQ instance is running. Same goes for PostgreSQL, MySQL, and Tanzu Greenplum as well. Since each of these are stateful applications, let's look at the storage tab and look at the different storage classes that have been configured. So looking at the Portworx RabbitMQ storage class that we have defined or deployed for our RabbitMQ instance, you will see that we need a replication factor of 2. So 2 copies of data needs to be stored with an IO priority of high. So as an operator, I can control all of these different settings and provide the features that my stateful application needs. Let's go to the namespace overview and let's, for example, look at the RabbitMQ namespace. So here you can see that we have a RabbitMQ instance that is deployed as a stateful set running. So by navigating to the stateful set section, you will see that we have one instance called Tanzu RabbitMQ get started server running. And as part of the configuration for that stateful set, it needs the desired state was set to 3 pods, and then as you can see, we have 3 running as well. If we navigate to individual pods, you can see that we have 3 different pods that participate in that stateful set, and then we have a perf test pod running in the same namespace to generate some data against our RabbitMQ instance. Looking at storage and persistent volume claims, each pod as part of the stateful set deploys or asks for a persistent volume that's 50 gig in size, and this is provisioned using the Portworx RabbitMQ storage class. And then if we look at since RabbitMQ is deployed using the Tanzu RabbitMQ data service, you can look at the custom resource and look at the connectivity between all of these different resources. So RabbitMQ since it's deployed using an operator, it's a custom resource that deploys a stateful set. Stateful set has pods in it, and then each pod has a persistent volume claim attached to it with additional things like secrets and service accounts that are created for our individual RabbitMQ pods. So everything looks green here, everything looks good. Our application is up and running with no operational issues. But now let's navigate to a different namespace where we have deployed a MySQL or a Tanzu MySQL instance. This is where Portworx really helps because, for instance, the RabbitMQ instance that we had high availability built in at the application level. So we had 3 pods, part of one stateful set. But then for MySQL, maybe this is just running my dev test workloads. I didn't deploy it with high availability. I just have one pod that is responsible for hosting my MySQL instance, which is part of a stateful set. So even for applications that don't have redundancy at the application layer, Portworx can still provide resiliency and redundancy at the storage layer. So looking at the persistent volume, it is using the px-mysql sc storage class, which has a replication factor of 3 that's defined for this instance. So even if my pod goes down, even if I lose a node, I won't have any data loss. And as soon as the pod is back online, I'll be able to access my database. Now let's log into the Portworx pod, exec into it, and then run a few commands to look at things like the Portworx cluster status. Here you can see we have the 5-node TKGS cluster, each node contributing 150 gigs of storage for a total capacity of 750 gigs. We can use pxctl or pixicuttle volume list, and you can see all the different persistent volumes that are deployed for different VMware Tanzu Data Services. Let's find the volume ID for the persistent volume for MySQL and do a volume inspect command using that volume ID. Here you can see that we have 3 replicas of data which exist on 3 different nodes. And then since MySQL is deployed using our Stork scheduler, which works in conjunction with Kubernetes, the pod is only deployed on a TKGS node, which has a replica or a copy of the persistent volume. So there is data locality intelligence built inside Portworx as well. Now let's run some workload against our RabbitMQ instance and our Postgres instance and perform some failover testing. So we started a RabbitMQ test. Let's open up a different PuTTY session and then exec into the PostgreSQL database for example, and then just use pgbench to generate some data against our test DB. So we use the username pgadmin and then create some entries for our Postgres instance and the table called testdb. So while this is happening, what we'll do is we'll identify the node that is hosting one of our RabbitMQ pods. So for that, we go back to Octant, go back to the pods tab, and then identify the node that's running, let's say the RabbitMQ get started server -1 pod. So we identify the name of the node, and then let's coordinate. So when we delete the pod, the original node is no longer available to be scheduled on. So let's use the simple kubectl coordin command for the node that's hosting the RabbitMQ get started server 1 pod. So again, it's a simple command. This basically disables scheduling on the worker node. Let's verify that the command worked. So as you can see, it shows scheduling disabled. Now let's delete the RabbitMQ one pod that's running in the RabbitMQ namespace. So kubectl delete tanzu RabbitMQ get started server -1 -n RabbitMQ, and then we'll force it so it doesn't have time to sync any data. So with a grace period of 0. So our pod is deleted. Let's do the same thing for PostgreSQL because we want to test both of these, like 2 different storage classes, 2 different namespaces. We want to make sure that Portworx, by using Portworx, you don't have any kind of data loss for any of your different stateful applications or Tanzu Data Services for that matter. So if we do a kubectl get pods on the RabbitMQ namespace, you will see that the 1 pod is now being spun up again, and it goes through an initialization error phase, and then finally it moves into the running stage. While it does that, let's go to the Postgres namespace and look at the status of our pod. As you can see, our pg-instance-example-1 pod is now running for the past 24 seconds, so everything looks good there. And then while the Postgres instance is already up, let's make sure that the RabbitMQ pod also came online. As you can see, it went through a couple of restarts, but our pod is now up and running. Since we are using Portworx, and the way we have configured VMware Tanzu RabbitMQ is that even when a node goes down, there won't be any data loss. The messages just get queued, and then when the node comes back online, the messages are written to disk. So there is no real data loss, or no data loss at all when it comes to VMware Tanzu RabbitMQ leveraging Portworx as the Kubernetes storage layer. So let's go back to Octant, and we'll try to navigate to the custom resource again and look at the resource viewer section to make sure everything is green again. Even after injecting failures into our Tanzu Data Services, we want to make sure that everything looks good, which it does. So that was a quick demo to highlight how you can leverage Portworx as your Kubernetes storage layer for all your different VMware Tanzu Data Services. Having such a uniform and a consistent storage layer makes it really easy on behalf of the operator or the DevOps admin to ensure that consistent policies are applied and consistent feature sets are applied across different stateful applications, or in this case, different VMware Tanzu Data Services. That's it for this demo. Thank you for watching.